physics of fluorophores in diverse environments. So time resolved data are usually obtained using either the time domain or the frequency domain method. And I'm going to talk a little bit about both of these methods. Although, as you'll see, once you get into using FLIM and phasors with FLIM, you don't really care what the method was. Nowadays, with instrumentation, you're distanced from those considerations, but it's nice to understand the basics of how these basic methods work. And as will be discussed later, phasor plots, and this is an important point, they can be constructed using either time domain or frequency domain data. And some people still don't understand that. They think, oh, you have to do frequency domain. That's not true. You can do it from time domain. So what is the time domain? Well, the time domain or impulse method, the sample is illuminated with a short pulse of light. Okay, we see here short relative to the fluorescence lifetime, and then you record the intensity versus time. So here we see it, and when the intensity goes down to 1/E of the starting intensity, normalized to 1, or 36.8%, that's called the lifetime. So you can see it's like a statistical property on many molecules. Now, let me anticipate. Some of you may say, well, how do you ever do single molecule lifetime? Well, you do that by exciting it again and again and again and again and again. Okay, because remember, lifetimes are so short, you can excite it thousands and thousands of times, okay, to accumulate the same sort of information. Now, let me say, originally, these short pulses were generated with flash lamps, which had widths of several nanoseconds. And that really made it complicated when the lifetime was short enough that you had to worry about the distortion of the curve by the flash lamp. And you had to, we call deconvolve or deconvolute the intensity decay from the flash lamp pulse. And in fact, this used to be a big deal. I've been to meetings. I remember a famous NATO conference once. I would say 80% of all the talks were about mathematical methods to extract the lifetime when you had these broad flash lamps. All that's in the past now because modern laser sources generate pulses with widths on the order of picoseconds or shorter, femtoseconds. And it's interesting because the only time you have to worry about then deconvolving the pulse from the fluorescence is when you want to look at the very, very, very early times of the process. And I always remember Gregor Weber telling me he was not interested in those early short times. He liked the public life of the fluorophores. He considered that the private life of the fluorophores, and he didn't want to go there. But nowadays people go there. So as shown in that intensity decay figure, we already said it's the time the intensity decays to 1/E. So the decay of the intensity with time is given by this equation where I of t, intensity at any time, is equal to a pre-exponential factor alpha times e to the minus t over tau, where tau is the lifetime. So it's more common to plot the decay with the logarithmic scale, as we see here. And here on a logarithmic scale, a single exponential will be a straight line. I should say it's not really necessary to do this anymore. In the old days, like when I was a student, you actually did this because you didn't have computers to fit it so easily. You did this, and then you would put a ruler on it and verify, oh, that's a single exponential decay, but you don't need to do that so much. So if it's multi-exponential, you're going to have several components, as we see here. The intensity at time t will be a function of more than one component. And in such a case, you may have data looking like this. This is simplistic, but you get the idea. You have a pulse, and this is still the log scale, but now you see a big curve in the scale. We have a short component and a longer component. Okay, so that's how this would look in a multi-component situation. And now I want to show you actual decay data for, in this case, anthracene and cyclohexane taken on a time-correlated single photon counting instrument. We'll talk about that method in a moment. Here, the the pulse is a short pulse diode laser. And we can see this is the exciting pulse in blue, and the red dots are the actual data points as a function of channels or time. And we can see when we start off at 10,000 counts, we go to 1,000, 110. We can see there's a lot of scatter in the points out here because we have very, very few points. Or, you know, obviously we're talking 10 points now, not 10,000. And the solid line is the best fit through those points. And the chi-squared is a measure of how good your data fits your model. So here we see the residual plot, it's called, and we see that the data as a function of each channel goes up and down randomly above the line. So that's considered good, and the chi-squared here is 1. A reduced chi-squared would be 1, would be good, perfect. But how do we actually get that again? Well, remember I said it's when the decay goes down to 36.8%, and on the log scale, that's 36.8%. In this case, there were 73 channels from the start to the 36.8 point, and it's 56 picoseconds per channel, so it's 73 times 0.056 nanoseconds, 4.1 nanoseconds, and that's how you get it. So that's how you would get the lifetime out of this sort of data. Obviously, if it's multi-component, you'd have to do a more complicated fit. So let me just briefly say some of the main points of the time correlated single photon counting method, which is probably the most popular method. We have a pulse light source, and then we have some electronics that monitor when those pulses come out. And the important thing for us is it goes into a time amplitude converter. And what I'm telling you is actually going to be not exactly the way we do it nowadays, but it gives the idea, I think. So the time amplitude converter has an output that depends on the receipt of a start pulse and a stop pulse. And the more delay between those pulses, the bigger the voltage of the output. So you start the pulse, let's say with the excitation, and then you have a sample compartment with filters, whatever, you're looking at the emission, and when you get an emission pulse, you stop it. So then you have an output and you store that count in what's called a multi-channel analyzer, a computer essentially now, and that you build up your curve. So for example, the first photon may go in this channel, the second over here, then the third over here, and you keep going and going, and eventually you build up the curve. So that's basically how we build up this curve right here, channel by channel. Well, in the old days, the flash lamps were relatively slow, like 40,000 flashes per second. And you're only allowed 1 photon per flash, and you don't get one every time. So it would take a long time to accumulate, but nowadays these laser and LED sources are very rapid. The classic one you use in the lab for film is 80 megahertz. So you can build these up much faster, okay? Now let's think about the harmonic method, also known as the phase and modulation or frequency domain method. Here you have a continuous light source, which is modulated sinusoidally. That's traditionally, I mean, now we have other ways to do this, but traditionally, let's think of a continuous source whose intensity or output is modulated sinusoidally, as we see here. And typically, well, I should say in the older days, and still today in many instruments, use a Paco cell electro-optic device to modulate this CW laser or xenon arc, but alternately, it's more common now to use light emitting diodes or laser diode at the wavelength you want. In such a case, the excitation frequency is described by this equation. The excitation intensity at time t is equal to the intensity at time 0 times 1 plus ME sine omega t. ME is the modulation factor. We'll talk about that more in a moment, which is related to the ratio of the AC-DC parts of the signal. I'll show you that in a moment. Omega is the angular modulation frequency. it's equal to 2 pi f, where f is the modulation, is the linear modulation frequency. So when I say we modulate at 20 megahertz, I'm talking about f, and then you could calculate what omega was. So this is a better way to look at this. So we see the excitation pulse here go, or excitation wave goes up and down. And due to the persistence of the excited state, the fluorophore builds up at the beginning, but that lasts longer than the excitation, and there's a shift in the phase. So we can see a shift between the excitation and emission, this phase shift. Okay. Now also we can see these AC-DC levels change. So we consider the DC level like the center point of this waveform, and the AC is how far you go above it or below it. And we see that changes in the emission too, because the emission's coming down and down, but it starts getting pumped up again. So we never come down all the way. So the AC-DC ratio of the emission actually changes also. And you can demonstrate that the fluorescence at time t in this format is equal to the starting one plus mf sine omega tau plus phase, where phase is the phase shift. Okay, and this phase delay forms the basis of one measurement of the lifetime. In particular, you can demonstrate that the tangent of the phase angle is equal to omega tau. So if you measure that phase angle, that phase shift, you can calculate the lifetime. But what about these modulations, these AC-DC ratios? Well, you have an AC-DC ratio for the excitation and one for the emission. And you can talk about a relative modulation then of those two modulations, for the emission and the excitation. And in fact, then you can determine tau from the modulation, from this equation, 1 over the square root of 1 plus omega tau squared. And that is the modulation lifetime, which can be different from the phase lifetime. Obviously, if there's only one lifetime in the solution, single exponential decay, phase and modulation lifetimes are identical, okay, at all frequencies. But if you have multiple components, which is by far the more common case, unfortunately, then you can see that tau phase will be less than tau modulation. And moreover, both values will depend on the modulation frequency. So I put this table in just to give you a feeling for what I'm saying. So suppose I have a mixture with two different fluorophores with different lifetimes. At 5 megahertz modulation, maybe I measure 6.76 nanoseconds by phase and 10.24 by modulation. At 10 megahertz, I measure 6.02, so I'm lower, and 9.7 by modulation. So we see phase is always less than modulation. And as we go to higher frequencies, both phase and modulation decrease. Well, these properties basically form the method to analyze the lifetime heterogeneity, how to analyze and determine the component lifetimes and their amplitudes. Okay, in the case I just showed, these were mixtures, two fluorophores of 12.08 nanoseconds and 1.38 with relative intensities of about 53 and 47%. Obviously, I was trying to make it up about 50-50. I'm sure I was doing this in the old days with Enrico when he first made the multi-frequency machine. You'll hear about that later. But here you have to distinguish, though, and this is very important, between fractional contributions to the total intensity and the pre-exponential function referred to later. So there's a relationship between them, okay? And basically, in this case, the ratio of the pre-exponential functions, what I just showed you, would be 1 over 8. And this means there's actually 8 times more molecules in solution with the 1.38 nanosecond lifetime than there are with the 12.08. But the fractional weight of the, let's say, the current reaching the detector from the phototube is more like 50-50. And it's traditional, it used to be more common to see frequency domain reporting fractions and time domain reporting pre-exponential amplitudes, which actually caused some confusion. Certainly I got caught in that once. But usually nowadays, if you're reporting such data, you would say if you're doing, they often report both of them. For example, in Uruguay, you have a very nice multi-frequency lifetime machine for cuvettes and from ISS, and they give you both values. But why the difference? Well, some people, let's say, are interested in how many molecules have a certain lifetime. Others of us often are more interested in what fraction of the photons I'm measuring have one lifetime and what fraction have another lifetime. Okay, but it depends what you're doing. So here's how typically multi-frequency phase and modulation data are presented. So we do this in multiple frequencies, and we see the phase goes to higher and higher phase angle as we get to longer frequencies, okay, because the tangent of the phase angle is equal to omega tau. And the relative modulation goes down and down. It would start at 1 and goes down and down as we go to higher frequencies. So in this case, these are the actual data points for fluorescein in buffer. And the bottom of my screen's blanked, but I believe it's like 4.1 nanoseconds or 4.05. But those are the solid lines that go through that. I wonder how I move my little, well, I won't move it. If I touch anything, I'm going to screw things up, so that's fine. But you get the idea. You fit the data points to different models, just as you do in the time domain. And this shows you that if you have single exponential decays, they'll have the same shape. They just move back and forth along the frequency axis. Here's 27 nanosecond lifetime by phase and modulation, 1.74 nanosecond lifetime by phase and modulation. And if we were to move them along the curve, they'd be superimposable. It's just they're shifted in frequency. But if you have more than one component, these shapes are distorted. Here we can see one component, phase and modulation, and here's two components, phase and modulation, okay, with different values, which are listed below. So to a practiced eye, you can really tell with your eye when you've done a lot of these, that when you have singular or multiple components, but you don't have to do it with your eye. You analyze by trying different models, okay? But all of these analysis methods require you to try different models, and you're going to see, especially when I think Enrico talks, that's one of the great things about phasors. You're not trying to fit models. I should mention that frequency domain data can also be acquired using the harmonic content of pulsed sources. So you can have a repetitive source. This is actually showing a synchrotron radiation to storage ring giving pulses. And basically, you can extract from that all the multi-frequency data, okay? And again, in the systems you're using in these microscopes, you have 80 megahertz pulses, and sometimes you can measure that using the harmonic content. Well, you'll see actually that, and you'll hear about that, if you have 80 megahertz, then you have a harmonic at 160 and at 240, and that can be important, as you hear about later. So let's talk about phasors now. So the concept of phasors has been around a long time. The original phasor transfer was an invention of Charles Steinmetz, who was a mathematician and engineer born in 1865. And he was very famous around the turn of the century. He knew everybody famous, like Einstein, Thomas Edison, etc. And he was an extraordinary mathematician and engineer, electrical engineer. And he introduced the concept of phase vectors, which he named phasors. That's where the word comes from, phase vectors. Specifically, he did it to facilitate analysis of RLC circuits, okay? So electrical circuits using algebraic equations in the phasor space instead of differential equations in the time domain. And in fact, if you just search phasors in PubMed, you'll pull up hundreds and hundreds. Sorry, there's a cat whining here in the background. You'll pull up hundreds and hundreds of articles about electrical phasors. So you should say phasors fluorescence if you want to get the ones we do. But the inspiration for phasors in fluorescence was connected to a paper by Gregorio Weber, in this paper, where the problem he was solving at this time was if you have phase and modulation data at 2 or more frequencies, can you extract analytically the lifetime, the underlying component lifetimes and their amplitudes? And in this paper, he put these equations for these G and S terms, which form the basis of phasors and frequency domain, and also time domain. Again, I stress you can do it either way. Well, the next thing happened in this review that I wrote with Enrico and Bob Hall many years ago. Enrico had the idea to put in this phasor diagram in the appendix. I had no idea what this was, but there it is. And this was the first phasor diagram for fluorescence, to my knowledge. But the idea of it at that time was to be able to demonstrate why, if you have a mixture with different single exponential decays, the one lifetime, the phase lifetime, will be shorter than the modulation. It's not easy to show algebraically, but it was relatively simple to show trigonometrically, and that's the figure that's also in the paper. But what was the first use in the lab? I think it was probably this paper with Greg Reinhardt, Brasquina, Marzola, Enrico, and I. And the issue was this. There was a lot of criticism of this frequency domain method in the early days by the time domain people, who said, well, you can't subtract the background. In the time domain, you simply put in the background solution, in these days, buffers, let's say, and you accumulate counts, and then you subtract those counts channel by channel from the fluorescence experiment. Well, in fact, in the using phase space, you can do this also, as shown here. You can have a background signal and then a sample, which gives you the composite. And if you measure the background phasor, you basically subtract it from the composite and you get the corrected sample phasor. And here we see this is on a tryptophan analog, N-acetyltryptophanamide. We can see what the background looked like, and here's the background with the sample, and here's the sample corrected. So it provided a way to correct that, which I think was an important point back then. Again, trying to establish parity between the two methods. Okay, actually a phasor approach was used by Lenny Brandt's lab in 1993. I didn't know this for many years. And here they showed that you could use this method to, in this case, study calcium binding to calcium chelating probes. But they had not seen the 1984 review nor the 1991 paper. Their work was completely independent, but they never named their plot, which is too bad. We would have had another name out there. So let's talk about the algebra of phasors. It's a slide from Enrico. So in phasors, all single exponential decays lie on this so-called universal circle, okay, which is formed by the phase angle and the modulation vector as you sweep through this with different lifetimes. But you'll hear more about this later. The basic point I want to make is that single exponential decays appear on this circle. And if you have a mixture of them, they're going to appear inside the universal circle. Okay, and you'll get actually they'll fall on the line between those 2 points, and the distance along this line will give you the fractional amount of one or the other. So immediately you can see the information you can get out of the phasor. Now, here's a nice program by Lorenzo, which I like a lot. So if you see on the left, you see when it starts, you start with one lifetime and blue, and then you start adding in another component. And on the right, you see where the little spot on the phasor diagram moves to. So look at the beginning, it starts all in the blue, and then as you're adding in the other shorter component, it moves over to the left. So it's a nice way to just visualize how these go. So I thank Lorenzo for that nice diagram. The phasor approach in fluorescence was around then since '84, but it was dormant till the last decade or so when several labs began to apply it to film, but with different names. These, okay, and we'll talk about them and the names. So the first representation with microscope was by Andrew Clayton, Quinn Bailey, and Peter Verveer. And interestingly, their point was to resolve two lifetime components in a film image with one light modulation frequency using Weber's 1981 algorithm that he presented in the paper I just showed you, okay? And they actually called this plot then the AB plot, which is not a very interesting name, I think all of us would say. And they presented AB plots using data from several film publications, but they never presented film images. Bob Clegg, though, 2005 with Redford, made what they call the polar plot, which again is the same concept. They didn't present film images, but they wrote that they've been applying this last few years to film data, but these were only in abstract, so we never saw it. And unfortunately for all of us, Bob Clegg died not too long after this, which was a real loss to the fluorescence community. He was an unbelievably talented person. So they have the polar plot. But Enrico introduced phasors, and what the phasor plot basically applied to film in his lecture, starting in these workshops in Genoa, sponsored by ISS. And there's, we see Enrico, and there's Beniamino, the president of ISS. There's me, Susana Sanchez. So that came up there. And also in 2006, he gave the first of his LFD workshops, which has now gone on every year since then. And he presented the definitive lecture on phasors, okay? So that really came up from them. You'll hear the new way phasors are used in FRET. But let me just mention that the approach he introduced was conceptually completely different from previous work on FLIMs and phasor-related plots. Specifically, the approach he introduced was to connect the phasors, the pixels in the FLIM image, to phasor points in the phasor plot. And you're going to see the enormous value of this. So this graphical method was transformational, I would say, in the FLIM field. Now, over the years, Enrico always invited me to the LFD advanced workshops. I presume for comic relief. All right. But I think it was during the 2008 workshop, I was listening to Enrico expound on the wonderful merits of phasors, which I admit I didn't really appreciate until then, when it occurred to me, wait just a damn minute. I could be doing all of this in a cuvette. You can see me right after I got tenure. Okay. So in fact, that happy thought kicked off a series of cuvette-based phasor measurements. And I'm going to show them because you guys won't see so much phasors in cuvettes, but it's still very good for these type of measurements. And I think it illustrates the power of the phasor method. So this paper we had was originally rejected from analytical chemistry because the reviewer didn't think phasor method was of any value. But fortunately, they were accepted in analytical biochemistry. And the early work was done with Martin Steffel, a graduate student from Czech Republic in my lab, my postdoc, Nick James, and Justin Ross, and I. And we even made the cover, which doesn't mean much nowadays because nobody ever sees the cover, do they? I only know we made the cover because they send me a copy of the journal. And some of the things we did then illustrate this very well, that here's at 20 megahertz, we're looking at phasors from 3 compound single exponential dyes of different lifetimes: DENS, about 30 nanoseconds, IEDANS, 5.3, rhodamine, 1.66. And if you start mixing them, and we mix them, you get, mixing 2 of them, you get these points along the line, or this line, or this line. If you mix all 3, you get these points going towards, you know, in the middle, inside of all these. So you can see how you can easily extract contributions from different components by looking at the positions along lines in the inside the universal circle. Now, with a multi-frequency machine, we could do different frequencies, anything we wanted. And the trick is to do the one that shows what you're looking for the best, because we don't usually do multi-frequency phasors, although I'll show some. So an early system we tested was what I had done in the paper testing Weber's algorithm. And I showed you Weber's 1981 paper. The paper following that was a paper with me and Gregorio Weber testing his algorithm. And we did it on tryptophan as a function of pH, because you get a shorter component form here, depending on the protonation. And when you deprotonate that amine, you get a longer component. And in between, it's simply the pH will determine the mixture of the fractional contributions of each to the mixture. So you can see you can have a pH 11, you're on the Euler circle, a pH 6, you're on it, and in between you just slide up and down with different pHs. And that was done at 25 megahertz, and this shows you at 15 megahertz the same thing, but you see it better at 25. So you pick the frequency that's best. And I must say, it's amazing to me that the lifetimes you usually do in FLIM really work great with that 80 megahertz laser, but that's another story. Here we see, as a function of quenching, it just moves along the universal circle as you quench it, gets shorter lifetimes. And if you have lysozyme, which has 6 tryptophans, most of the fluorescence is from 2 of them, you're inside the universal circle, but again, you get 1 point, and it moves when you quench it. Doesn't matter how many tryptophans. Here we see some work. I do a lot of work on dynamin, 5 tryptophans. Here's the dynamin phasor. When you add GDP or GTP, it moves. So you can see you're disrupting the conformation, disrupting 1 or more of those dynamins. Here's monomeric human serum albumin. When you add thyroxine or furosemide, that moves too. In fact, I bring this point out because many people in the literature have used HSA right from the bottle, lyophilized, and you always get about 15% of dimer HSA. And you can see there's a difference in the lifetime. So for God's sakes, if you're doing HSA purify, get monomer, not right from the bottle, which is in a lot of the literature. Here shows if you have 2 proteins mixing, like we have 2 proteins that don't mix, lysozyme and antithrombin, and we could mix those 2 together, and the phasor point, you'll still get 1 point, but it'll be along the line. And here you see thrombin and antithrombin, they interact, and when they interact, the points move off the line. So it also is a method to look at protein interactions without labeling. You don't care how many tryptophans are that, and I'll show you an example later. Now here, looking at the denaturation of lysozyme with urea or guanidine, and we see the pathway is quite different between them. And here's some work of Felipe Montesinos, who was from Chile, and he came to my lab in Hawaii, and now he's at the NIH, and he did urea unfolding of this single tryptophan protein FITZ. Actually, it has no tryptophan, he put 1 in, and we can expand that. You can see you get very distinct and reproducible points. So you can really follow stages in these denaturation things. And he even made 3-dimensional plots where you can look at urea on the left or guanidine, and of course in the computer you can rotate these. And here's the actual data here. Back here is the projection of this on a 2-dimensional plane. But the 3-dimensional data, you can see different stages. You can see it's quite different, guanidine and urea, and it was kind of interesting to look. And these are 3 different single tryptophan versions of that protein. But it was really nice to have this tool to study these processes. Again, here we're not interested in the lifetime value per se, but we want to see the process that's taking place. Now, here's a nice plot from one of Bob Clegg's paper, which is relevant to us, where he shows what happens with FRET. And we see here we have a donor 3 nanoseconds, and as we quench it by FRET to an acceptor, the donor lifetime goes down and down. But actually, if we were to look at the acceptor getting excited by the donor, it goes outside the universal circle, which is an important point. Processes that happen during the excited state create an additional phase delay that takes you outside of the circle. Okay, and I'm going to show that to you here. This is a demonstration of something you can do with phasors that's enormously difficult to do otherwise. So there's 1 tryptophan in the classical wild type GFP, green fluorescent protein. You'll learn more about that later, of course, from Richard Day's talk. and there's the chromophore. But if I ask you, can this tryptophan have energy transfer to the chromophore? That's not easy to say. Normally, to see if there's energy transfer, you would look at the donor in the absence of the acceptor. But in this case, the acceptor is built into the molecule. Well, we can do it very easily with phasors. So here's the universal circle with the GFP points looking at that exciting at 471, looking at the emission of the fluorophore, the chromophore above 500, at a series of frequencies. Okay, and all the phasor points are on the universal circle. Now, though, we're going to excite at 280, which excites the tryptophan. But again, look at the phasor points from the chromophore, and they're outside the universal circle. They can only be outside if there was an excited state process. So this proves, yes, there's energy transfer, and it's very difficult to show that any other way. So this illustrates one of the powers of the phasors. Here we see it in lipid vesicles, and you'll hear a lot more about membranes and phasors from Lionel and others. And you can see, if we're looking at temperatures where we have Lordan in this case, and you're at the phasor, it's outside the universal circle because we're having relaxation of, I talked about that dipolar relaxation around the excited Lordan. And here's some work that Lionel actually did this data in my lab when he was a graduate student, and not to pick on him, but I don't think this is published yet, but that's another story. But we can see again, you can't analyze this data using single exponential decays. They're non-exponential, but using the phasor method, you can track what's happening, in this case, as a function of different lipids with different cholesterols and different temperatures. And it's just such a nice method to follow these processes. And I just want to show this one. Jose Lopez was a Brazilian postdoc in my lab, and he had a peptide that had two tryptophans in it. And when they bind to mice cells, it changes. You can see from the free to the bound, you can titrate in and the phasor points shift. And here we see on this diagram, that section expanded. So I said, how do you analyze this for a binding curve? Well, of course, you look at the Pythagorean theorem. You look at the diagonal. And when you apply that and plot using the Pythagorean theorem, you get a beautiful binding isotherm. Again, all from these phasor points moving. And again, we don't care how complex they are. And the final example was done in Uruguay with Matthias Moller, Joachim, Sebastian, and Anna De Nicola. This is in the lab where they have that ISS multi-frequency. They wanted to know if this decamer dissociates into dimer to follow the process. Well, they've done it other ways, but these have 2 tryptophans per dimer. And in fact, normally, if you want to study the tryptophan in there, you'd go at 300 nanometers, but that's much less absorption than at 280. But with phasors, we don't care. So you excite at 280, you don't even collect all the emission. You don't care how complex it is. You're just hoping that the phasor or the lifetime changes when it goes under decamer to dimer, and it does, okay? And as you dilute it, it goes down and down. And I thought in the beginning this downward curvature was dimer to monomer, but they tell me this is not the case. They've got cleaner buffers and it goes straight out. But look at this. You're just following the dissociation easily, and this just takes minutes to do this. You measure phasor, dilute, measure phasors, dilute, measure phasors, dilute, and you get these degrees of dissociation match, and it's easy to change temperature. So it's really a nice method. Now, again, with phlegm, we mentioned Enrico's phasor approach basically can go from phasor point in the pixels to pixels lifetime points to where they are in the phasor plot. And you'll see a lot of work how you can distinguish. This is obviously not taken all at once, but where NADH would appear free and bound, retinol, et cetera, different things. So there's all these different methods. And I have to acknowledge, of course, Nick, James, and Justin in my lab, and Martin Steffel for their work, and Felipe Montesinos, and Jose, and Lionel, of course, and Matthias, Joachim, Sebastian, and Anna for all their help. And of course, we have to thank a big mahalo to Enrico Gattone. So that's it. And I think I'm on time, Leah, now.